All right, here's the beginning of the last big section, couple of topics that we have for BC Calc, all done remotely, but do come with questions to class, and we'll roll with those. So intro to parametric and vector calculus. So the first thing we'll do is parametric. Parametric means like you're talking about a parameter. It really is reference to a new parameter added to these equations. So if I just take a basic function that we know, like y equals 3 minus 2x, that is an equation kind of. It's like it's been there since the end of time. It has the slope of -2, y-intercept of 3, things that you can pick up on just looking at it. But what's interesting is where did it come from? How was it drawn? How fast was it drawn? Those are questions that become interesting, and we can answer if we use some kind of parameter. In this case, time. We do all of our work with the parameter of time, but we can use others. You can see above. Just read the piece. We can talk about all kinds of with reference to variables and talk about how things change and also how things are graphed. Well, we're going to do time. So if I put this graph, I'm kind of interested in, well, how was it laid out? What order was it laid out? How fast was it drawn out? Where did my pen start? How fast did it move? And parametric equations can answer that. So let's move forward to this example on here. I'm just rewriting what I just said in the same, but a third variable called the parameter, and it's something to do with usually time for us, and that's just the BC standard. Now, I think we can now talk about, again, how fast it was traced and in what direction, and that's where we're going to go with this. So we're going to graph old-fashioned ways. We're going to do a table. So we're going to take this create set of parametric equations, and they'll come in sets, an x and a y, so that you can end up plotting it the same way. And when we're done, we'll also write out the traditional equation that would model the picture of what's left, what would represent it. So that's all to kind of tie things together with what you know with what's new in this whole parametric thing, which actually I think you probably have some experience with via some of your other classes. So now, here we go, t(x) and y. We're going to use t as our kind of counter. So t is going to move from -2 to 3. I'm going to choose integer values just because it's easy, but there's no reason we couldn't put in fractional or decimal values and do things in smaller increments, but I'm choosing to do it by integers. When we do this by your graphing calculators, you can change up the steps of your t variable. So let's go -2, -1, 0, and 1, and look at the points that we can plot. Now, I plugged it into the x variable and then into the y variable. Got these values. You can test them yourself. It's just plugging in the t into those functions. And then you get coordinate points. They're classic coordinate points. 0, -1, got it. -3, -1/2, got it. -4, 0, plotted. -3, 1/2, done. So are you starting to see something that looks familiar? Maybe if you predicted it looks like kind of a sideways parabola, and you'd be right. So keep going, 2, 0, 1, 3, 5, and 1.5. Now here's what's cool. If you look at, we're making step sizes in t of 1 integer value, and I chose that so you could look at x and y, and notice they don't make step size in a consistent value. So the first one went from 0 to -3, that's a jump of 3. Then it went from -3 to -4, jump of 1. Then another jump of 1. Then a jump of 3. Then a jump of 5 from 0 to 5. Are you noticing there's kind of a speed change as you make the bend around the corner? We kind of start, you get a sense of, we start with -2 as our first time. Are you kind of picturing in your mind where this is getting, where it's going to if you're kind of tracing in order? Well, that's the idea of a parametric, is we can trace out that order, and we can get a sense of how fast it's moving by these leaps that happen between, these ones, let's say they're 1 second time intervals. Let's say time is in seconds. We're seeing some leaps of different amounts. That's a different rate if it leaps further, yet over the same amount of time. So here goes. There's the rest of it. We want to put in the direction now. You got the idea. It's kind of going around the bend there. When you get to 0, -4, right before then we had this, my time went up 1, and I seemed to move 1 x variable. So my horizontal motion was 1. So that's kind of a 1-to-1 rate of 1. But then you go from, maybe the points -3, 1/2 to 0, 1. My x jumps up 3 spaces in that same time. It means it's moving a little faster to get there. Same time, moved further. So that's the idea of, now we have a sense of where we started, what direction we plotted it in, and we have a sense of how fast. Now you get the idea. If we want to really know how fast it moves, might be a derivative involved in there, then you'd be thinking right. So here you go, to the calculator. When we get to class, this is the online piece that you guys are watching just to get the idea. We're going to play with the calculators, let's say tomorrow, to when you're watching this. Maybe it's not, maybe it's the same day. but you want to get your calculators ready, we're going to pull up parametric mode and start graphing these and seeing what we can do with that handy tool. Okay, so here's the deal. Also, these problems at the very top here, what do you notice about these graphs? That's what we're going to use to kind of mess around with our parametric graph. So hang tight, we won't do that right away. But let's look at these. This is what we just went over. Recap here. While rectangular equations on a restricted interval show the path, parametric equations show the path, direction, and speed. So much more information and kind of helpful. So let's roll with this. Now, the thing we didn't do on that last problem is we didn't come up with the actual the actual function, that sideways parabola of our graph in example 1. Well, here's how you do that. We call it eliminating the parameter. We actually solve for t in one of the equations. It doesn't matter which, however, there's definitely an easier one to choose in most cases. And then you take that solved for t function and you put it into the other parametric equation. And so we're going to substitute that right back. And you can also use other methods of systems of equations to solve for these variables. It's kind of, we're just using what we'd call substitution to solve for it, but that tends to be the easiest route. So let's put it, so these are the two parametrics. We'll solve for, I think, the easiest one without the squared. I don't like taking squareds if I don't have to. So t equals 2y, our second equation. Now we can put that in for t in the x equation. There you are, and if we do a little distribution, there's our nice looking function. Now if you notice, that's like it kind of looks like a parabola, but it's on its side because we're doing a function of y, and this is x in terms of y, so it's sideways. And the 4y squared, that ends up being a horizontal stretch of 4, kind of like because we're turning it on its side. And the minus 4 ends up being a left, kind of a shift left 4. The graph is moved down on the graph. So the ones that we saw before, it's just a sideways parabola. And we're using parameter swapping the variables and looking at it from that direction. Now you guys know that's not a function, right? We're dealing with not passing the vertical line test. So parametric equations can carve out non-function representations of curves, and it does a pretty darn good job of it. So here we are again. This is x equals 4y squared minus 4, which looks just like what we had, except it's the whole function. Ours was limited to going from certain t values, so it only carved out part of the equation. So the difference is this is the infinite curve, the whole thing. Parametric equations will be bound by some domain limit, or some just limiting values. If it's given explicitly, that's pretty easy. That's what ours was. Put in t values from 0 to, I think it was 0 to 3, right? Or we put those values in. That's the only part of the graph we can get. We can use smaller increments between the two endpoints of the interval. However, we can't go beyond those. Now, when they're not given, which we'll see in the next example, there's something else we do. But this is more graph, but a little bit of the parametric limited graph is something we noticed. There it is. Yeah, I finally put it in there. That was when we put those green dots in there. Those, we could say, you know, our x equals 4y squared minus 4 is the same as our parametric graph if we limit y to -1 to 1.5, including -1, not including 1.5. So here we go. So in class, let's talk about graphing these and show you the difference in the similarities between these. It's kind of a fun little exercise and gets us acquainted with the calculator, but again, later. Second example. So if not given, if I don't have an interval given, you actually have to use the shared domain. There are limits, so just put together all the things that x can and cannot be. If you notice, -1 is a pretty obvious candidate. It can't be -1. But less obvious, of course, is you can't take the square root of a negative. So that left square root of t plus 1, that's going to give us some domain issues. So not equal to 1, and we can't have t be anything less than -1. So we could say t is greater than -1. Taking the square root of 0 would make dividing by 0, so that's bad. And any square root of a negative would be bad. So it has to be bigger than -1. That ends up being our domain. We're going to use that. So here's some values. Let's try it out. Starting with something easy. You can start with -0.9999999 if you want, but we're going to start with something relatively easy, and we can always fill in points later on. And just choose easy stuff to get started. Choose things that when we take the square root, you don't have to think too hard. We want to get the picture of what's going on. So if I choose 0, and for t I get 1 and 0 for x and y. If I choose 3 for t, then I get a nice square root, perfect square underneath that radical, so it's 1/2 and 3/4. And same kind of idea, I'll choose 8 because it gives me a perfect square under the radical. check these out. This is kind of wild. Are you noticing where this is headed? It's kind of getting closer and closer to, do you notice y is 3/4, 8/9, 15/16. And if we continue this on, you'll notice a pattern. It's just going to continually go where the numerator is 1 smaller than the denominator. So you're always going to get something less than 1. So it's approaching 1. Y is approaching 1 as t goes on and on and on, t to infinity. So this, we can describe this in terms of a limit, of course. So we're just headed towards 1. The limit that would go with this, t to infinity, of t over t plus 1 is 1. That's something you can note numerically, and or you can use some fun stuff we know, like, hey, those coefficients of t and t are 1 over 1, so the limit as t goes to infinity is 1. Good thing to keep in mind. This doesn't start here. We started with 0 as our first parameter value, but we can back up a little bit, so let's pick something else that might work. Get a little picture of what's going on before that first point. Let's put in 1/2. Okay, that's greater than -1. 1/2 goes in. I get, because it's also, again, I can get something I can square root. So I get the square root of 2, -1. Yeah, there it is. Let's pick another one. Does that do it for us? You're noticing that's a pretty good leap there, a little bit bigger than the last leap, square root of 2 to 1 and 1 to 1/2. So we're seeing square root of 2 is over 1. So we're seeing a 1. Then we can do some more. If you see, it's kind of coming in from negative infinity. If I put in even something like 0.999, something close to 1, you're going to be taking the square root of something that's pretty small. And as you take the square root of something that's pretty small, what we're seeing is we're taking 1 over super small. We can get as small as we want in that x parameter. That means we're going to be coming in from infinity, the x variable. If you do the same for the y variable, if I put in something really close to -1, like -0.9999, that numerator gets exceedingly small, which means y is also going to be negative infinity. So that's interesting. So we're looking at a graph that kind of shoots in from negative infinity and then comes up to 1 but never goes past it. And it has implications for the rate. Like you have kind of a finite amount of rate in the middle there, but toward the ends, you're seeing kind of infinitely slow and infinitely fast, respectively, for the rate of change in and around infinity for x. Kind of the right-hand side. If you go down here, maybe I should put a little highlight down. As we go down, we're seeing some infinite values for location and for rate of change. As we head towards 1, this thing's kind of slowing to a stop. Okay, on we go. We'll graph that on the calculator too and play with it a little bit next time. We want to get to the function. So the last thing you do is you always want to eliminate the parameter and talk about what's this function. It's an upside down parabola, so I think we have in our mind something negative x squared-ish. So when we do that, solve for t in one of them. I think the right hand is easier. So if I do that, check this out. Here's a few steps at once. I should probably pause that here for a second. Sorry, I meant to put a stop in there. The multiply both sides by t plus 1, distribute the y, factor out the t, or actually factor out the t. And then what do we got? Something like t times, I think that looks reasonable. I put the t on both sides. Oh, sorry, I left a step off of there. I'm supposed to put t on the other side. Swap these two guys. Okay, I should put a better color in here. Sorry, got to swap these two. And then when you swap those, then we get this function down here. And t equals y minus 1, which equals negative y. Divide both sides by t. There we go. Thanks, I knew I left a step off in there somewhere. Negative y over y minus 1. And that's it. We can put that into the other function. It's not easy. It goes under that radical. That's all right. We can handle it. So I'm going to flip it around too, because you know it's a square root. I don't want to deal with negatives, so I'm just going to go ahead and take that negative y and put it into the denominator and just swap the position of the y and the negative 1 and change their signs. So see that in red there. Hopefully that makes sense to you. So now I can sub that into the other equation. We can do some solving because we want to get down to a function of x and y that's readable. I'm going to go ahead and square out the square root because we don't want squares in the denominator. So let's square both sides. Okay, so here we are squaring both sides. And you guys know if we have this situation, you can get out of one of these rational function denominator things by multiplying by the denominator helps usually multiplying out, so we can get that rational function out of there. So I'm multiplying by the 1 minus y top and bottom. Cleans things up a little bit, so you can see this little dude. And once it's cleaned up, We get some cancellation of the y's. That's pretty slick. Bam and bam. And 1 minus y over 1. There it is. X squared equals 1 minus y. So yeah, it's not quite what we want. Let's solve it for y, because I think that would look more, we want this upside down parabola. We're used to seeing it like this, right? Y equals negative x squared plus 1. Well, that's part of it. Our particular parametric doesn't have the whole function, so what we'd want to do is say our parametric is modeled by y equals negative x squared plus 1, but we need to restrict the domain to being simply x greater than 0, because you notice in our graph it stops once we reach the y-axis. That's the idea. That's the kickstart to this whole business. Some problems that we're going to do, you can take a look at the problems I gave to you. Go ahead and tackle as much as you're comfortable with. Trying to graph those, solve. We'll move into the next one pretty shortly. See you soon.